Welcome back. I'm Steve Brunton from the University of Washington, and I'm incredibly excited to kick off a new video series on optimization. This is my Optimization Bootcamp, and I've been planning this for about the last 10 years. So ever since I started the Control Theory Bootcamp and my lecture series on machine learning and singular value decomposition, in the back of my mind, I've known that I've wanted to do this lecture on optimization because optimization is the mathematical engine that powers the modern world. Perhaps even more than linear algebra and calculus, optimization is kind of the mathematical backbone of almost everything we do in industry, in agriculture, in finance. It is ubiquitous. And so in this series, I'm going to walk you through kind of the applications and mathematical methods of optimization with special examples in machine learning and control theory, and a lot of interesting mathematical concepts along the way. So let's get started. We, in general, are going to be talking about optimization problems that have a mathematical form where you're trying to minimize some objective function f over some variables x. Now, this could be a minimization problem or a maximization problem. So I could also do max of f of x with respect to x, but usually I'm going to pose this as a minimization. And this could be something like a cost minimization or minimizing the error of a machine learning fit. And this is only one half of an optimization problem. The second half is that there are some constraint equations that limit what x's are valid for the solution of this optimization problem. So you have your objective function up here, and you have your constraint equations that limit what possible values of x your state can take when you're optimizing. And these can be very physical constraints, like let's say I'm designing the wing of an airplane to have the maximum lift and the minimum drag. There are clearly constraints on the weight of the wing, how long it is given the strength of different materials, all kinds of constraints that you would have. Okay, and we're going to talk a lot about this at length. This is the overview video, so I'm just giving you kind of the mile-high view of some of the topics we're going to cover, why they're important, and this is the starting point. This is the optimization problem. This is the standard form of an optimization problem, and we're going to keep coming back to this over and over and over, looking at different examples of F and G and H, different kind of case studies in machine learning and control theory of what these constraints are, what our objective function is, and given different kind of types of optimization problems, maybe, f is a convex function, then we would have this kind of convex optimization problem. Given different properties of the objective function and the constraint equations, we have broad categories of optimization problems. I'm going to show you what those are, why they're useful, and how to solve them. Good, so before I go too much farther, I want to show you some of the amazing applications of optimization. Pretty much any machine learning model that has ever been trained was trained using optimization under the hood. Essentially, at the simplest formulation, when you train a machine learning model, like a neural network, you are adjusting the weights and the parameters of this model to minimize some error and some other terms in an objective function. So this would be the error of the machine learning model, and you're going to minimize over the weights, in this case of a neural network, to minimize this, the sum of the square of the errors of this model averaged over the training data. Every machine learning model you've ever seen has been trained using optimization. So, we all know that machine learning is this kind of huge new endeavor and set of tools for humans to use for things like language processing, ChatGPT, image generation, movie generation, super resolution, you name it, protein folding, protein discovery. Every single machine learning model that has ever been trained, essentially, is trained using optimization, okay? Most of the modern neural networks are trained using some variant of a stochastic gradient descent. And again, I'm going to tell you why we would use that, when we would use that, and how to use it. The simpler kind of, cousin of machine learning is simple least squares regression. So before we were doing deep neural networks, we were training kind of really, really simple models, these least squares regression models. So lots of statistical models, Bayesian models, principal components analysis models are based on this linear least squares regression, which again, you solve using optimization. And this is one example of an optimization problem that actually has a closed form solution. So we could actually compute the gradient of this function and set it equal to 0. That's one of the conditions for optimality. And you could solve for the x's that minimize this error of the model fit in closed form analytically. So this is going to be kind of a lighthouse example, the least squares problem, where you actually can solve the problem. Okay, so all of machine learning, every machine learning model you've ever seen, all of least squares fits into the camp of optimization. Also, almost all of control theory, basically every single problem in control theory is an optimization problem. And it's a really cool optimization. It's an optimization problem constrained by the dynamics of your system. So I might be trying to find some optimal controller that spends as little energy as possible to stabilize my system, constrained by the dynamics of the system, constrained by the fact that there's some differential equation that actually governs the dynamics of my system. So my entire control theory bootcamp fits under this kind of umbrella of applied optimization. All of my lectures on least squares and singular value decomposition and machine learning fit under this umbrella of optimization. And in the real world, in the kind of applied industrial world, in the manufacturing world, where you actually build devices and things, NVIDIA chips and Intel chips, Boeing aircraft, these are hard optimization problems. How do you pack transistors on a chip and optimize it for performance and heat dissipation and latency of communication? A modern aircraft like the 787 is a huge achievement in optimization. If you think about this, it is approximately 20% more energy efficient than historical aircraft designs. This requires advances in aerodynamic shape optimization, in material science, both in the wing and the body, but also in the engine for the blades. It requires optimization of the engine itself. So all across the board, systems engineering is kind of based on this foundation of multi-objective optimization. Okay, optimization is the cornerstone of the modern industrial world. I'm going to have a whole lecture on applications. We're going to go a lot deeper, but I just wanted to, get you thinking all of machine learning, all of control theory, most of manufacturing, material science, industrial design, aerospace, aerodynamic shape optimization of cars, of planes, of trains, all of it at the end of the day is an optimization constrained in many cases by physics, by the physics of the real world. Very, very kind of important concept. Okay, back to math. So we're talking about this optimization problem in particular. Minimize some objective function, maybe the drag of a wing, subject to some constraint equations. And I've written this objective function. In the simplest case, we're just going to say that we have one objective we're trying to either minimize or maximize. But in the real world, we're going to have complicated multi-objective optimization problems, and we'll talk more about that later. Okay, so what do I mean by f of x and g of x and h of x? So generally speaking, my cost landscape, my objective function landscape f, is going to be pretty messy. It might be high dimensional. It might have lots of local minima and saddle points and local maxima. Like for example, if I'm training a machine learning model, the variables x that I'm optimizing over, there might be a million free parameters I'm trying to tune in a neural network. So x might be a million dimensional, and I can't picture this landscape. This is just a cartoon. And there might be tons of local minima, saddle points. The landscape might be really messy, okay? So that's my objective function. Sometimes it'll be simple. Like in the least squares problem, it'll just be a simple paraboloid, okay? And these constraint equations, whatever the constraints on my system are, those set up what is called a feasible region. We have it visualized here in purple. A feasible region or a feasible set of values that x can take and satisfy these constraints. So now the objective is try to find out of this feasible region, try to search around this feasible region for the x that minimizes my objective function. And here in this picture, you can kind of do this in your head. You can see where this minimum would be in that feasible set. In more complicated, higher dimensional problems, we're not going to be able to picture it or draw it or visualize it. And so we're going to need mathematical algorithms to find the minimum of f of x subject to these constraints. And there's a lot of properties of f and the constraint equations that would make this easier or harder. So the example I've shown here is what's called a non-convex optimization problem, because literally the function f of x is not a convex function. We'll define what we mean by convex later, but this has lots of local minima. It doesn't have one nice global minimum solution. And so this is a non-convex problem. This is on the harder side of optimization problems when you have non-convexity. But there's still tons of things we can do to solve these problems. So for example, we can compute the gradient of our function f oftentimes. Sometimes we can't. Sometimes f is so messy we can't even compute its gradient. But oftentimes we can compute the gradient or approximate the gradient. And that tells us the direction in which the function increases the fastest. So if I take steps in the gradient f direction, I will climb my function as fast as possible. So we're going to have a whole series of lectures on the geometry of the gradient and the tangent approximation to this function f, and how you would use that gradient to do things like gradient descent. So for example, if I take steps in the minus grad f direction, I will descend my function as fast as possible to a local minimum. So this is how most machine learning neural networks are actually trained, is using a stochastic gradient descent. In that case, f and its gradient might be really, really high dimensional and nasty, so we approximate the gradient using a stochastic gradient descent. And again, we'll talk a lot more about that later. Now, if I have a simpler cost function f, here what we visualize this kind of parabolic cost function, this is what's known as a convex function. So if my objective function is convex and my set of feasible points is also convex, then we have some pretty profound guarantees in optimization theory. So there's a whole huge category of convex optimization problems. It's the largest set of problems where we know how to solve them in scalable, computationally tractable ways, is when we have convexity. And you have this kind of cornerstone result. If you have a convex objective function f and a convex feasible set c, given by these constraint equations, then if you find a local minimum of your function, it is also a global minimum. And this is a huge result. So whatever algorithm you use to find this local minimum, whether it's a gradient descent or you set grad f of x equal to 0 and solve for x, if you find a local minimum of a convex optimization problem, it's guaranteed to be the best global minimum you could possibly find. That's a huge deal. And this is the basis of like a huge branch of mathematics called convex optimization theory. Okay? Kind of like in differential equations, we know that linear differential equations are like the broad category of differential equations where we have analytic solutions. Convex optimization problems are kind of that type of problem in convex optimization. Okay, so it's not so much about linear versus nonlinear in optimization, it's about convex versus non-convex. So we'll spend a lot of time talking about convex optimization. And specifically, I'm going to have a whole set of maybe 5 or 10 lectures on what does it mean for a set to be convex, what does it mean for my constraint equations to give me a feasible region that's convex or non-convex, and what does it mean for my objective function to be either convex or non-convex. So we're going to talk a lot about this. I'm going to build your intuition with simple examples. We're going to work problems, and we're going to use this to find out when our problem is or is not convex, and when we get all of those guarantees. And 2 of the biggest categories of convex optimization problems are what are known as linear programming and quadratic programming problems. So in both cases, these are huge kind of categories of optimization problems. Again, entire books have been written on linear programming. This is one of the most industrially used optimization algorithms on the planet. Basically every, supply chain optimization, agricultural optimization, how you lay out a factory floor or plan airline scheduling, those are all linear programs. Finance and risk management, hedge funds are very often posed as linear programs. This case, you have a linear objective function, so that's a really nice, easy, class of linear objective functions, and linear inequality constraint equations. So that's why it's called linear programming, and there's very powerful techniques to find optimal solutions here that scale to very large problems. Quadratic programming is another massive class of problems we're going to talk about. So the entire category of least squares regression fits into this quadratic programming framework, where, let's say, the error of a least squares fit can be written as a quadratic cost function. Okay, and here again we would have this subject to these inequality constraints. Sometimes we would have these, sometimes we wouldn't. So again, very often I will solve an optimization problem with no constraint equation. So I'll have like a really simple, I'll have no constraints, and my feasible region will be all of Rn, all of the n-dimensional vector space that my state x lives in. But sometimes I will have constraints, and I'll have to constrain my optimization to some feasible set. And when I have linear inequality constraints like this, my feasible set is going to be one of these geometric kind of polytopes, which generalize, polygons to n-dimensional spaces. Okay, we'll talk a lot about this. I'll have like mini boot camps on linear programming and quadratic programming. Okay, and again, backing it up, we still have this broad category of non-convex objective functions and non-convex feasible sets. So we're going to need to also talk about how do we approach these problems when we know that our optimization problem is non-convex. In general, training a neural network is a non-convex problem. And so we do have increasingly powerful techniques to solve non-convex problems. And that's actually been a big advance in the last 10 or 20 years in optimization theory. Before that, we really didn't have a lot of chances with nasty non-convex problems. Increasingly, we're being able to take non-convex systems and either relax them to nearby convex problems or find innovative ways of finding good, maybe not optimal, but good local solutions using things like stochastic gradient descent. So we'll talk about all of that later. Okay, good. So that's the Optimization Bootcamp. This is really going to be a series of mini boot camps. I'm thinking, the core Optimization Bootcamp will be probably about 10 hours, but I'm guessing there will be at least 10 or 20 additional hours of mini boot camps following on. There is going to be a set of lecture notes, maybe a textbook that goes with this. So, you can either download that or purchase that and follow along. Hopefully it's out by the time these videos come out. And it all comes down to this mathematical form. This mathematical form encompasses so much of how we kind of optimize and fine-tune the modern world: supply chains, transportation networks, industrial designs, machine learning training, control theory, you name it. This humble mathematical formulation here is probably one of the most important concepts in the modern world. So what we're going to see next, I'll have a set of overview videos that'll talk about the geometry of the gradient. We'll talk about convexity. We'll talk about kind of a little bit more about the anatomy of this optimization problem and the applications of optimization in the real world. And then we'll get into gradient-based optimization, things like gradient descent, stochastic gradient descent, Newton's methods, and things like that. So iterative methods when you can maybe compute grad f, but you can't solve for when grad f equals 0 analytically. So when the gradient of f is equal to 0, that's when you have kind of a flat tangent plane with 0 slope, and that's one of the conditions for a local optimum solution. So gradient-based methods are going to try to iteratively walk my system towards a point x where grad f equals 0. Okay, we'll talk a lot about this. All of machine learning training is, typically using gradient-based methods. Then we'll get into kind of more classical convex optimization theory, like linear programming and quadratic programming, things like least squares and constrained least squares. This is going to be really nice, huge categories of very useful techniques that are intuitive, easy to understand, and we've seen a lot of these before. Then we'll go into constraints and duality. This is a really important abstract concept in optimization. So a lot of the ways that we handle these constraint equations is by kind of using Lagrange multipliers. If you've seen Lagrange multipliers before, we're going to get deep into it here, where you basically take these constraint equations and you add them to the objective function with a Lagrange multiplier multiplying that constraint term. And so we'll talk about constraints, Lagrange multipliers, and dual forms of optimization problems. Oftentimes, there are dual versions of your optimization problem where it's easier to solve. Okay, so we'll talk about this. but really you can think, Lagrange multipliers. And then we'll talk generically about non-convex optimization problems. So, gradient-based methods actually do apply to non-convex problems, but you can almost think of this as like special topics in non-convex optimization. What do you do when you have really nasty non-convex systems? And then we'll get into some of the applications, which is where, my heart really lives, is things like inverse problems. So there are a whole host, basically all inverse problems can be posed as optimization problems. So let's say I'm trying to estimate what a black hole looks like from satellite images, from incomplete satellite images, or I'm trying to estimate the mass of a black hole from incomplete information. Or I'm trying to do some kind of seismic inversion. Let's say I have my seismographs across the globe reading out different readings. Can I localize where an earthquake occurred? Or heaven forbid, a nuclear test? Okay, that's a huge category of inverse problems. Very, very important, and almost all of them can be posed as optimization problems. And specifically, if I have prior physical knowledge about the system, I can pose them as Bayesian optimization or Bayesian inverse problems. So these will be kind of two very closely related but different topics, inverse problems and Bayesian optimization. And then we'll get into kind of where a lot of my research and time gets spent is how optimization is used in control theory and how optimization is used in machine learning. So again, this will tie into my optimization bootcamp, but I'm going to get under the hood. How do the algorithms actually run? How do you derive the Riccati equation? How do you derive and show that the Kalman filter is an optimal estimator given certain assumptions on the noise and the dynamics? So all of this is coming up. I'm going to try to feather a little bit of history along the way because I find history so motivating and fascinating. I mean, you can guarantee when the Egyptians were building the pyramids, somebody was optimizing, some aspects of supply chains and routes and workforces. I guarantee you. I mean, we don't know for sure, like we don't have the records, but I can guarantee you somebody was doing some kind of an optimization. And it might be kind of clever to think, were they doing linear programming or some rudimentary version of that? I don't know. But, I'm sure that ancient Egypt, Rome, and the modern world were built on optimization. Okay? All of this is coming up. This is going to be one of the most powerful tools in your arsenal, and it's going to change how you view the world. Thank you.